within the horizontal plane, there are two components. So we can align, we can measure those two components in any two orthogonal directions. Generally we measure north, south and east, west direction. We align our instrument in such a way that these two horizontal components and then one vertical component, these three components we are measuring. So we get one time history record in north-south direction, another time history record in east-west direction. And using vector resolution, we can get the ground motion records in any other direction. At any angle alpha, I can get this ground motion from these two records. Okay. Now, if we are using time history analysis, where we are using ground motions directly, then we can just consider these two components and automatically the directionality of the earthquake will be considered. But when we are using response spectrum we obtain for one ground motion record. So you will have one response spectrum here, another response spectrum for this ground motion, and this response spectrum is going to be different. Okay. So one of the questions is which response spectrum I should use. To show you how the response in different directions is changing, okay. So if you take a single degree freedom system, so we have a single degree freedom system, I put a pin at the top of this. It is subjected to earthquake motion in the two orthogonal directions. Okay, and at top of it, I take a glass, I put a glass plate, and on this glass plate I put a carbon layer. Okay, using kind of earlier, if you go to our seismological laboratory, you will see the old records. So when they were recording earlier, what they were doing, there was a glass, sorry, not glass, a paper. On the paper, they were putting a carbon layer using simply a lamp. So the carbon layer is put on that, and then the instrument was having a needle. So that needle was scratching that. Okay. So this will show you the trace, the response of the single degree freedom system you can record on this glass. And because we are applying ground motions, it is put on the ground. So whatever ground motion is occurring in the horizontal plane, that will be considered. That will be traced on this. Okay. You can also do analytically, numerically. How? You just this, you analyze for two components of the ground motion. So in place of 1 degree of freedom, you have 2 degrees of freedom in the two directions. One in north-south direction, another in east-west direction. Okay. Or any two ortho. Then when you take the response, let us say ux and uy, so at any instant you will have ux and uy both. So coordinate system, here you take ux, here you take uy, you can plot that movement, how it is moving. Okay, at any instant of time you will know the location of the single degree freedom system in terms of ux and uy, and you can plot different values of ux and uy, you will get this type of plot. Okay, so this is the response of single degree freedom system in 2 dimensions. Okay, while performing the analysis in a plane. So for a real earthquake, two earthquakes rather, these plots are there. So this is Chichi earthquake recorded at a particular station, HWA031, that is the recording. This is for another earthquake, Morgan Hill 1984 earthquake, and it was recorded at this station, Gillory Array number 6. So this station it was recorded. If you look at it, here you see that in almost all the directions, the response is, the peak response is more or less similar. Okay. But in some of the directions it may be less. It is not exactly equal in all the directions. But if you see this, then the response is only in one direction. In the other direction, the response is very small. Okay. This effect, which you see here, this is called directivity effect. What we were discussing was directionality. This is directivity. Okay. So let us say this is the fault on which earthquake is occurring, and I have two sites. One site is here and another site is here. So when the rupture occurs at any site, okay, it does not occur simultaneously over the whole length. It starts from the hypocenter and then it moves. Let us say hypocenter was here and the rupture is moving in this direction. Okay, and from here the pulses which will generate, those are also moving like this when it is reaching. So our wave is also traveling in this direction, the rupture is also traveling in this direction. So first wave will start from here, then after some time from some other point this wave will start. Like that a number of waves will be starting from here, and there will be constructive and destructive interference. So here the waves will be going from different points. So you can see that the phase in the two cases is going to be different between the different pulses of the earthquake which are reaching my site. So the characteristics of ground motion here and here will be different. So those sites which are along the alignment of the fault, those will be experiencing different type of earthquake, this will be experiencing different types of earthquake. So in one particular direction, the earthquake may be much stronger, earthquake intensity may be much stronger, the component in the perpendicular direction can be much smaller. This is called directivity effect. Okay, so here you have significant directivity effect. You can also call it as polarized ground motion. Like you have polarized light. In general, the light is having vibrations, those are electromagnetic vibrations, but those electromagnetic vibrations are in space, in the 3 dimension, okay, perpendicular to the movement of the wave. But when you put or you polarize the light, it has vibrations in one plane. Okay, so same thing you can see that it is in this plane, it is occurring, and perpendicular to it, it is small. So this directionality is very important. In some earthquake it may be like this, in other earthquake it may be like this. Okay, if I have to design a building and I know that this type of motion is going to occur, I can design my building stronger in this direction and weaker in this direction. Still it will be safe. I need not to design my building stronger in both the directions. But if this type of motion is there, my building has to be stronger in all the directions. Okay, I have to design for the same response spectrum in all the directions. This is relatively new understanding, and this type of information is not available for all the earthquakes. Okay, the orientation of the faults is also not very clearly available. Okay, so in some cases, very few cases, you will be having this information available to you, and there you can use the directivity effect or the directionality of earthquake you can take into account. Most of the cases we will be dealing this type of situation. Now here, which response spectrum I will use? That was the question which I posed you, I left you with in the last class. So what do you think? Anybody tried to Google or do something? Okay, so no need, I'm here to tell you. So, but at least you might have thought what should be done. If you have to design for this, what should be done?
Consider the maximum response.
Consider the maximum response spectrum. Okay, how you are going to get the maximum response spectrum? So there is a maximum response spectrum. What is this maximum response spectrum? It is giving the maximum response of a single degree freedom system which can occur in any direction. Okay? So for that single degree freedom system, out of that full record, whatever is the maximum response in any direction, that is obtained. How you are going to obtain this? For that, you have to take the two records which you have obtained from the instrumentation and then consider different directions here, these different values of alpha, and then you can obtain the ground motion in this direction. Okay? Consider all the directions from 0 to 180. And then plot response spectra in different directions. And these response spectra you plot together . Okay, then two possibilities, or rather three possibilities are there. One is this envelope, the maximum, another is this minimum envelope, and third one is the median. You understand this process, what we are doing? The recording is done in two directions only. You need only two ground motion records. Those are representing the ground motion fully. It's not that you have to record in other directions also. But from those two components themselves, you can generate ground motions in different directions by simple vector resolution. And for each ground motion or ground motion in each direction, you can get a response spectrum. Response spectra are going to be different. At some period, one response spectrum may govern, and another period some other may govern. Okay. So one possibility is that we consider the maximum. This maximum is also called ROT D100 spectrum. The median is called ROT D50. ROT D100 means that it has 100% confidence. In any other direction, the response spectrum is not going to exceed this. Okay, in any direction, the response spectrum is not going to exceed this. So that is ROT D100, ROT D50, and ROT D00. This is also called maximum response spectrum. Okay. In some of the attenuation relationships, they are using rod D50, median value. In some codes, for example, in ASC7, this is used. In some other codes, geometric mean of response spectra in two orthogonal directions. Like in our code, a response spectrum is given. When that was given, this concept of rod D100 and rod D50 was not there. Most probably it is not documented, so I cannot say it for sure, but most probably it is geometric mean, what is given in our code. Nowadays, advanced codes like ASC7, USGS, United States Geological Society, they are using rod D100 and rod D50, these definitions.
The same geometric mean is used in the revised code also.
I'm not sure. Have you read? I have not read it. We have to look in the code. It might have been mentioned, it might not have been mentioned. Most probably they are using rod D100, because now attenuation relationships for rod D100 are available. So it will depend upon which attenuation relationships they have used. Okay. So how to obtain the design response spectrum, what is given in the code? This process we call seismic hazard assessment or seismic hazard analysis. Two methods of seismic hazard assessment are available: deterministic in short we call it DSHA, and the probabilistic. PSHA. Our current code, IS 1893 Part 1, 2016, is based on DSHA. The revised code, which is under revision, under wide circulation, which is going to come in few months, that is based on PSHA, probabilistic seismic hazard assessment. So we have just transited, or rather transiting from DSHA to PSHA. Okay. As the name itself suggests, deterministic seismic hazard assessment means it will give you one value of hazard. And what is that one value? The expected maximum hazard or maximum intensity of ground shaking. Intensity can be represented by either PGA, which is actually EPGA. We are using effective peak ground acceleration, not PGA. So intensity can be represented just by EPGA or with full response spectrum. So using DSHA, we can obtain either PGA or any spectral ordinate, SA at 1 second, SA at 0.2 second, like that, or the full response spectrum. Okay. In probabilistic seismic hazard assessment, we obtain different labels of seismic intensity, hazard. Seismic intensity itself we call hazard. We discussed what is hazard. So hazard is intensity of ground shaking. So different levels of seismic hazard or seismic intensity corresponding to different probability of accidents or different return periods. In DSHA, there is no concept of probability of accidents or return period. In PSHA, different return periods will lead to different response spectra, different PGA, okay, different intensity, any of the intensity measure that will vary. Okay, so this is the difference. These two you can learn, the details of these you can learn in a course. There is a full semester course on seismic hazard assessment. So I do not know if any of you have taken that course. If you are taking that course, then you will learn these details there. Okay, here we will do a very simple exercise just to give you an idea that how the process is done, okay, of deterministic seismic hazard assessment. Once you understand that, then you can extrapolate yourself what we may be doing in probabilistic seismic hazard assessment. It is not possible to teach the full concept here because it's in itself it is a full semester course. Okay, but any structural engineer, okay, so this full semester course or this job of seismic hazard assessment is done by a seismologist. So you know, in our department there are three branches. One is engineering seismology, geotechnical engineering, and structural engineering. Okay, structures will be designed by geotechnical engineers and structural engineers. But what hazard, design hazard will be used, okay, PSHA and DSHA, this will be done by seismologists. So seismologists, the job of seismologist in design of structures is to provide the design seismic hazard corresponding to any return period or a deterministic value. Deterministic value is sort of theoretical maximum, what you are expecting as the maximum seismic hazard there. And in PSHA, you can get corresponding to different probabilities of accidents within the lifespan of the structure. Lifespan of the structure generally we take 50 years. So within 50 years, what is the probability of accidents? And that probability of accidents can also correspond to an average return period. Okay, we will talk about that in more. I will just discuss a little bit about deterministic seismic hazard assessment so that you can communicate with the seismologist. So in deterministic seismic hazard assessment, the first step is to identify all the sources of earthquake in the vicinity of the site. Meaning that those sources, earthquake at which can affect my structure at my site. So those which are far away, even if a large magnitude earthquake occurs there, the intensity at my site will be very low. Okay, so I am not interested in those. I am interested in those which can affect my site. And this vicinity is considered as the radius of roughly 300 kilometers. So from my site, within a radius of 300 kilometers, all the faults I will identify. Okay. So these sources, these are also known as active faults. Active faults are those which can cause earthquake in future. There may be some passive fault. So those were active at some time, but there is no evidence that they can cause earthquake in future. Those I can ignore, although it is a very tricky question. People are not able to identify what is active, what is passive. Okay, it's very difficult. But if you know that this is passive, you can ignore it. So active faults which can cause earthquake in future, all those faults I can identify. Now, do you have any idea how the faults will be identified? How can you identify the faults? You mean plate boundary? So plate boundary is not the only fault. Okay, faults are there in whole of the area. I mean, even intra-plate faults are also there. So it's not that just the geometry of the plates you plot, that is the fault, that is the source. Okay, faults can be inside the plate also. Okay, so one way of looking at it is the previous record of earthquake. From previous record of earthquake, what do you know? What do you get? A ground motion. So from there, how you can identify a fault? Okay, then what we can do? From the epicenter, how will I know the source?
Sir, above the epicenter, there will be, we can directly reach to the, some team of survey can reach and therefore they can identify.
So you can plot the epicenters on a map, and wherever there is a fault, active fault, you will get a cluster of epicenters. Okay, but if you really look at that map, it is difficult. It is not easy, because different epicenters can be associated with different faults. So it is difficult to tell that which fault this particular epicenter is. So these will not occur along a line. These will be randomly distributed again. So there will be clusters, okay, but not that easy.
So by sending signals and bouncing back, and then difference in their velocity.
This is called seismological tomography. Like you might have heard CAT scan. Okay, in body. So what they are doing? They are sending X-rays from different directions, and from reflection on refraction of those X-rays, they try to identify what is inside the body. Same thing we try to do in case of Earth, but from that we can determine only what are the layers. We can't identify fault, because transmitting waves up to that distance will require a lot of energy. Okay, such energy can be generated only with a huge bomb blast. Then you can get that information. Otherwise, these small energies which we are creating by using a hammer or a small impact, sometimes people are using even a truck, okay, to cause that impact. The energy caused there will give very low intensity waves which can't travel those long distances. So this is done to study the local soil conditions, but this can't be used to study the crust of the earth. Okay, so one way of looking at the crust of earth is during earthquake, because earthquake itself is like a big bomb blast. It is causing waves in all the directions. Those waves sometimes are taking rounds of the earth. So that is one way looking at those. Okay, from satellite imagery, what will you get? So there is a term called lineament. So from satellite you can identify lineament. What is lineament? That a line like a structure. So if you find a line on the earth's surface that may, not always, in some cases, that may represent a fault. So the first thing we can do is a lineament. Now, important question is whether that lineament is representing a fault or this is due to some other natural phenomena. That lineament, a line, it's not that wherever a line you see, you declare it as a fault. Okay. So there is an organization called Geological Survey of India. Okay, they dig along these lineaments, they study the geology there, and they try to identify the forensic evidences that when, if any earthquake has occurred there, because if there is a movement has occurred, that can be identified by looking at the geology along that lineament. So satellite can only help us in mapping that. Okay, but whether that is a fault and then whether that is an active fault or not, for that we need more studies. Okay, so that is done by Geological Survey of India. And then Geological Survey of India has been working on this for more than 60-70 years. Actually, Geological Survey of India, it was established in the British era to study the minerals within the country. So whatever minerals, how much mineral is available for that. Then during earthquake, Geological Survey of India took surveys of those earthquakes. It plotted the intensity, the subjective intensity, different MSK, MSI, EMS. EMS is relatively recent, it was not there, so MSK scale was used. MMI scale was used. So using MMI and MSK scale, they plotted the maps of intensity of earthquake. And slowly people there, they became involved in study of faults also and study of earthquakes also. So it has what we call a seismotectonic atlas of India. A copy of that is available in our library. You can have a look how this atlas looks like. So all the known faults are mapped in this atlas. Okay, so they have all the faults which have been identified so far. Those are mapped in this atlas, and it is an unfinished job because more and more faults you may be discovering. But lot of information is available, a good confidence about identifying different faults and lineaments they have given in this atlas. So this can be one source of identifying different earthquakes within the vicinity. And then of course, as you said, the past recorded earthquakes. Okay, this is called catalog, a catalog of earthquakes. This cataloging of earthquake is done by IMD. What is IMD? Indian Meteorological Department. So IMD does cataloging, GSI does mapping. So longitude and latitude of all the past earthquakes which have been recorded or which were mentioned in some historical documents. Okay, those catalog IMD has prepared for the country. It can be downloaded from the site of IMD. Okay, so this is the first. You can plot the sources of different earthquakes which have occurred in the past. That will give you an idea where a source may be. Then you can relate those to some of these lineaments which have been plotted by GSI. So you can see that along this line where the fault is shown in this atlas, faults are shown by line. So along which line these recorded earthquakes are aligning with. Okay, so you can associate those to that particular fault. That is our first step. Second step is characterizing the source. What are the characteristics of a source? First of all, its potential. Which largest magnitude earthquake it can cause. So magnitude of earthquake. Okay. Then what type of rupture is occurring? Type of rupture mechanism means, you might have heard these terms: normal fault, reverse fault, dip slip fault, strike slip fault, and oblique fault. What does that mean? Within the earth, the fault is a plane. Okay? So this fault can be represented by two coordinates. Okay? One coordinate is, if you take the projection of this at the surface, okay, so it will give you a direction, bearing of this fault. This is called a strike. Strike is bearing. In surveying you have done bearing, how much angle it is making from the north. So to define a fault, you need to define two things. What is the bearing? That means if you take surface projection of this as a line, okay, what angle that line is making from north. So that is a strike. And another is dip. Dip is the angle which it is making from horizontal, okay, or it's perpendicular. If you draw a perpendicular to this, then what angle this perpendicular is having from the vertical or horizontal. So this direction is a strike, and this direction is dip. Okay, you can think it like this. If I have the fault like this, okay, so this is the orientation. So this orientation with respect to north is giving me the strike, and this angle, this is giving me the dip. So this is the dip direction. So if I say strike slip fault, what does that mean? That the movement is occurring in this direction. When I say dip slip fault, movement is occurring like this. What is oblique? Normally we will have oblique where both strike and dip slip will occur. So on a fault here, I am drawing the two blocks of the rock, earth crust, which are separated by this fault. This we call foot wall, and this we call hanging wall. How do we decide which one is foot wall or hanging wall? You try to stand on the fault. Then on the block on which your foot will be resting, okay, that is foot wall. And the other wall is hanging wall. Okay, for example, if this was inclined in this direction, then the foot wall and hanging wall will change. Okay, and it has been found that the earthquake intensity on foot wall side is different, hanging wall side is different. So earthquake is occurring at this fault. the motion caused on this side is different, the motion caused on this side is different. Okay. And if the movement is occurring like this, the hanging wall is going down relative to the foot wall, then this is normal fault. Normal fault. If it is opposite of it, this is reverse fault. Why this movement is occurring? Why the movement is occurring? Because of motion of tectonic plate. Okay. So from tectonic plate motion, what happens? Not always the foot wall is sinking. In the first case, the hanging wall was going down. So these tectonic plates, you know, world is divided into different tectonic plates. Those tectonic plates are moving in different directions. Somewhere those are moving like this, somewhere those are moving like this, somewhere those are moving like this, and somewhere it may be inclined. It's moving this as well as in this direction. So due to that complex movement of the plates, different types of stresses will develop on the fault. Okay. This movement will occur in shear. And what is the role of compression here? That will decide how much friction force will develop here. So on any plane, two types of stresses are there in a solid: normal stresses and shear stresses. So this will depend, this movement will depend on both the stresses, normal as well as shear. When the shear stress will exceed the shear capacity of the rock at that fault, okay, there will be slip. And when that slip is occurring, it is occurring in a jerky manner. It is not occurring smoothly, okay, because it is a brittle material. If earth was made of a metal, let us say steel, ductile material, then what would have happened? Shall we get earthquake then? No, because it is ductile material. And in ductile material, what will happen? The slow, smooth movement will occur. But because it is brittle material, so what will happen? Till it fails, it will go on taking the loads, and suddenly it will fail. And when it fails suddenly, it will cause a jerk. And that jerk travels to my site. And it is not only one jerk, several jerks. One jerk will occur, and as I said, that rupture is, it is like an unzipping failure. So this will start from one point, and there is a speed by which this jerk will, this rupturing movement will proceed. Okay? And pulse after pulse will be originated from this fault. And when those pulses are reaching at my site, that is causing a ground motion. That ground motion is earthquake. Okay? So this will depend upon this normal stress also. Now out of the two faults, which one you think will occur at larger stress, larger shear stress, normal or reverse? Which will require larger stress to occur? And whichever is occurring in the larger stress will be able to release more energy. More energy means higher intensity of earthquake. So which one can cause larger magnitude earthquakes? Reverse? Why? Why the reverse? In high school, you have studied an example which is taught of a roller in ground or making the pitch. There are two ways. One is you push the roller, another is you pull the roller. in which case you have to apply more force? Pushing. Why?
We have work against the gravity.
Sorry?
We have to work against the gravity.
Work against the gravity. Why work against the gravity?
No component of like.
The gravity is same in both the cases, whether you are pulling or pushing.
In
The friction of pushing is more, so the friction,
Why the friction is more in pushing?
because the component of pushing applies a normal friction.
So when you are pushing it, your force is in downward direction. So it has a component vertically downward, which is adding to the gravity, and hence the friction force is more. When you are pulling it, there is a force in this direction which has a vertical component upward, which is acting against the gravity. Okay, so the gravity force, net force is reduced, and due to that the friction is also reduced. Same thing is happening here. When the shear force is acting like this, you can see that it will have a component in the horizontal direction. If you resolve this in horizontal and vertical direction, you can see that there is a component which is acting away from the fault. So the effective normal stress is going to reduce at the fault. Whereas here you can see that the components are, the components are like this. So there is a component towards the fault. So here more energy will be stored before failure, before rupture, and if more energy is stored, more energy will release. So how much energy can be stored here will depend upon how much friction is available. That will depend on rock, that is earth crust, strength. Stronger rock, wherever earth crust is stronger, larger energy can be stored and larger magnitude earthquake will occur. When the earth crust is weaker, okay, frequent earthquakes will occur, but the intensity of those earthquakes is going to be less. That's why the characteristics of these different faults will be very different. It depends on so many things. Okay, so the magnitude of the earthquake which can occur, frequency at which those earthquakes are occurring, those will vary from place to place, fault to fault, because it will depend upon the type of the earth crust. Earth crust is not uniform throughout. Okay, so it will depend upon the earth crust and also the stresses which are developing there, the rate at which those stresses are developing. So these tectonic plates within the crust of the earth, these are moving with different speeds in different directions. So that's why the pattern of earthquake is different. Different faults are behaving differently. So each fault need to be characterized. Characterized means what maximum magnitude can occur, what is the source mechanism at which it is occurring. Okay, so that need to be known. Then the third step is identify path characteristics. What are path characteristics? First of all, the distance. R. So magnitude of earthquake which can occur in that fault and R. These are the two most important parameters, M and R. Okay, so M-R pair, this defines the intensity. A larger magnitude earthquake occurring at larger distance will cause less intensity. Even a smaller earthquakes occurring very close can cause larger intensity. Okay, so it depends upon M and R, and then it will also depend on the type of earth crust through which the earthquake motion is traveling. So earth crust in different parts of the world is different. it has been formed at different times, it has been formed by different processes in the surface of the earth. So the earth crust is not uniform, it is also varying. Okay, in some places there are very strong rocks in the earth crust. For example, in some part of the US there is very strong earth crust. Such a strong earth crust is not available in Europe or India. Okay, so it will also depend. Formation of Himalayas is totally different. Okay, so the type of the earth crust we are having is very different there, and then it will also depend upon the local soil conditions. The movement of the earthquake wave in rock and soil is very different. In rock, the velocity is very high, the frequency is also high. In soil, the velocity is low, the frequency is also low. Okay. Moreover, in soil, the attenuation will be very fast. In rock, it can travel long distances before diminishing, before dissipating all the energy. In soil, it will dissipate energy very fast, because in the soil, the damping is much more as compared to that in rock. In the rock, the damping is less. So any energy you input in rock, it can travel very long distances. In soil, it will travel very less distances. So that you need to consider. Then you determine response spectra or PGA or any other intensity measure in which you are interested due to different sources at the site. So you know MR. How we can take into account the path characteristics? By considering different region, in which region the fault and the site, in which region of the world. Okay, and this response spectra or PGA or this is obtained using what we call predictive relationships. What are these predictive relationships? These are empirical relationships. Empirical relationships between the intensity measure, okay, and the magnitude, the distance, and the path characteristics. How we can obtain such relationships? From past earthquakes. So for the past earthquakes, we know magnitude, we know the records at different distances from the epicenter, so we know the distance, we know the local soil conditions at that location where this record was recorded, the ground motion was recorded. We also know the regional characteristics. So these will vary from region to region because path characteristics will vary. Okay? So we have regional predictive relationships. Okay? And these are obtained from regression of past earthquake data. And when we obtain from past regression of past earthquake data, these are also called attenuation. The more common name is attenuation relationships. What does this word attenuation means? What this conveys to you? the energy is released at the hypocenter, okay, or at the fault. From the fault, as you go away, the energy goes on reducing, or the intensity of energy goes on reducing. Why? It is similar to if you have a bulb here. As you go away, okay, the light intensity will go on reducing. Why? How? How the energy from that bulb is dissipated? Okay, so if you think of sun to earth, is there any medium before earth atmosphere? So it is not colliding with any particle, there is no dissipation, but will the intensity of light same near the sun and near our atmosphere? Why not?
Because some amount of energy is being utilized in order for traveling.
No, in vacuum, in space, it is vacuum. Okay, so it is not. You have to understand that when energy starts from any point and it travels in all the directions. From this source, the energy is traveling, it is traveling in all the directions. Okay, so if you take a sphere here, the surface area of the sphere will be less. But if you take a sphere here, the surface area of that sphere is going to be large. And intensity is energy per unit area. So because this area is increasing, the energy is getting distributed in larger and larger area. Okay, so its intensity will reduce. Even if the material is not affecting it. But in case of earthquake wave, as I said, earthquake waves are not electromagnetic waves. These are elastic waves, and when these are traveling in the medium, these are causing vibration of the particles of that medium, and when the particles are vibrating in the medium, those are dissipating energy through damping. Okay, so there is additional dissipation of energy because of the damping of the material. So both these phenomena, distribution of the energy in larger area and material dissipation of energy, will lead to attenuation of the intensity. So this is called attenuation relationship. So you can understand that for a given magnitude of earthquake, if I take intensity and with distance, initially it will be large and then it will be dissipated, and it will be asymptotic. Okay, so using attenuation relationships, you can identify the intensity measure, and these attenuation relationships are obtained from past earthquakes. Last step, fifth step, plot an envelope. Of PGA or response spectrum. Okay, this plot or the peak envelope response spectrum may be due to one source, which we call as governing earthquake. Sometimes it may be due to two or more earthquakes also. In some period range, one earthquake may be governing. In another period range, it is possible that another earthquake may govern. So in that case, we have to take envelope of the two response spectra. By chance, if more than two are also governing, okay, then we can take envelope of these three. So the envelope of all the sources we have to take. Most of the cases, it will be governed by one single earthquake. Okay, so that earthquake we call governing earthquake, which is governing the intensity or hazard at my site. Okay, so we will stop here. When we meet day after tomorrow, tomorrow's class, that extra class, I will not be able to take. So day after tomorrow when we will make, I will give you some examples of simple attenuation relationships. And then I have already given a question in the tutorial. We will do that, okay, in class as much as we can to illustrate this deterministic seismic hazard assessment, DSH. Thank you.